Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be continuing our discussion of the Michelson and Morley. In our previous discussion, I kind of set the stage for the Michelson-Morley experiment by recalling a few predictions that had been made, for example, by Maxwell, but also by other 19th century scientists concerning the idea of the ether and its motion relative to the Earth. I discussed the Michelson original experiment as well as the modification from Michelson and Morley, in which they essentially rotated the Michelson interferometer to look for fringe shifts as the interferometer rotates. And this was basically to rule out the possibility of there being, let's say, a null result as per Michelson's original experiment due to the misorientation of the two arms relative to the Earth's motion, or due to other effects like moving the interferometer around kind of risked moving the relative position of the two mirrors and how far away they were from the beam splitter. So the Michelson-Morley experiment put the entire thing on a sandstone slab, which was then floated on a pool of mercury and could be sort of freely rotated with minimal friction and minimal vibration, and without having to physically reset all the components of the interferometer, which would in turn change lengths of the interferometer. So today's video, what we're wanting to do is kind of look at the math, basically the equations behind this experiment and what they predict, and thus get some idea of what Michelson sort of expected to see, assuming that the ether was not being dragged by the Earth. And so let's get into that. Basically, to explain the predictions that are being made by this experiment, we return to this diagram which shows the basic setup of the Michelson interferometer. Again, recall that it's on a sandstone slab. Recall that they give a torque to the slab. They give it a push that gives a torque to it, so it spins. It spins through, let's say, a complete revolution. So at some time during that revolution, if the Earth is moving, mirror M2 should be basically aligned parallel to the Earth's velocity and mirror M1 perpendicular. And then after a quarter revolution from that time, M2 will be perpendicular to the Earth's velocity and M1 will be parallel or anti-parallel. It doesn't actually matter which, since the beam actually makes a round trip. So it goes to M2 and then it comes back from M2. It goes to M1, it comes back from M1. So whether we're parallel or anti-parallel doesn't actually matter. So we basically are interested in what happens at these two times. For what it's worth, this basically should tell us what the maximum shift in fringes is, or what the maximum change is between the two arms as far as delay time for the beam to go from the interferometer's beam splitter to mirror 2, as opposed to from the beam splitter to mirror 1 and back in both cases. So what we kind of expect to have happen is, if this is the time axis and this right here is the sort of let's say, phase shift between the two. So I'll call this phase shift. We basically expect the plot to be basically sinusoidal. Okay, and so this right here might represent, let's call this like case or time 1 and case or time 2. So this would represent case 1 or time 1. So it would represent case 2 or time 2. And here we're back to, we could call this one actually like 1 prime and 2 prime. And then by the time we get back to the time axis, we're kind of back to whatever the original condition is. So this right here would actually kind of represent what would happen if the Earth is moving along this green arrow. And so the crossings here, 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 etc., these would be a condition, I call it the green arrow condition because I've drawn the arrow in green, but basically it represents the case where the beam does this. Here's mirror 1, here's mirror 2, and then the Earth's actual velocity is either like this or like this. So this is Earth's velocity for these zero crossings. And so basically what they would do is just, they'd need to sort of observe the relative fringe shifts between both ends. It turns out that their apparatus had a resolution of something like 0.01 fringe shift. So they could detect as little as 0.01 fringe shift. Now, what is it that they expected to see, assuming, let's say, a stationary ether relative to the Earth's motion about the Sun? So at this point in time, they're working with Earth's motion about the Sun. You could also do the calculation for Earth and Sun's motion about the galaxy, and I think that a later experiment called the Kennedy-Thorndike experiment basically did attempt to also consider the Earth's motion about the galaxy. This was a later experiment, of course, and actually accounted for some ideas like time dilation that the original Michelson Morley experiment did not account for and actually wouldn't have been aware of. So you can go look that one up if you want as a sort of like further reading. Coming back to the Michelson Morley experiment, what were the sort of expectations for this? Well, let's say that we have sort of case 1 where this we could call like arm 2 and this we could call arm 1, and so the path that's being traveled along each of those would have some amount of time taken. So delta t for arm 1 in case 1 basically would have just been whatever the length of the arm is. So let's come back to this. Let's note that each arm has some length L associated with it. And so L represents the distance traveled from the beam splitter to the mirror and then back. So time taken to do that should be 2 times whatever the length is that's being traveled, or whatever the distance is, divided by the speed. So we could call that like just speed. We'll represent it as speed. And so, okay, this is perpendicular to the Earth. And so what would the actual speed be, or what would the headwind speed be for this particular arm? Well, the speed when we're sort of perpendicular to the Earth should be obtainable just using simple vector addition for velocities. And so if we're looking for this speed of sort of like the speed that we care about here, this would be the v, then that's going to be given by this speed squared minus this speed squared, since this is a right triangle. And so you'd have square root essentially of c squared minus v Earth squared. And then for the arm 2, basically you have on when you're moving parallel versus when you're moving perpendicular to the Earth's motion, you'd basically have a delta t for arm 2 of distance, and then sort of going to it, you have this speed, and then going away from it, you'd have something like this speed. So if we wanted to combine this into a single fraction, basically we would have c plus ve L plus c minus ve L, all divided by c plus ve times c minus ve. And so if you kind of combine like terms here, the top reduces to c times L times 2, and the bottom is actually kind of a difference of squares kind of thing. So you'd have c squared minus v squared. And so that is your difference between top and bottom in case 1. So now we ask, okay, how much faster is arm 1 than arm 2, or vice versa? And the way that you can do that is you can get a sort of delta t between arm 2 and arm 1. And since 1 is actually the slightly faster overall, it takes less time. So what we would do here is we would subtract the smaller time from the larger time, for example. So this would be t arm 2 minus delta t arm 1. And basically we're just subtracting this from this. So what we have is 2cl over c squared minus v squared, or v Earth squared, minus 2l over root c squared minus v Earth squared. So that gives you your total time difference between the two arms in the sort of like case 1 orientation, where arm 2 is parallel, or for that matter anti-parallel to the Earth's motion through the ether, and arm 1 is parallel, or is perpendicular to the Earth's motion. And after a quarter revolution, basically all the math here remains the same. It just kind of flips, and so this entire thing ends up negative of what you have here. So what does the time difference have to do with anything? Well, in some sense, that's telling us how much phase difference we're going to have between the two arms. If you go back and watch the discussion in the original interferometers video, then you know that this difference in phase is what determines whether you have constructive or destructive interference at a given point in space. So as an aside, we can simplify both of these expressions a little bit by sort of dividing and multiplying by a common factor. So this one, if I sort of divide out a c squared from both terms here, essentially c squared minus v earth squared can be written as c squared times 1 minus v earth squared over c squared. And so that works for both of these. And the end result is that this term ends up essentially being, if I cancel this c with one of the two squareds here, this term ends up being 2l over c times 1 minus v earth squared over c squared quantity to the minus 1. By like reasoning, this term is 2l over c times 1 minus v earth squared over c squared to the minus half power. So my total delta t max simplifies down to 2l over c times 1 minus v earth squared over c squared to the minus 1 minus 1 minus v earth squared over c squared to the minus 1/2. And so that ends up being sort of your actual delta t max value. Now we can add one more detail, which is that you can do what's called a Taylor expansion. And that basically converts this square root guy into a polynomial, and it likewise can actually convert this guy into a polynomial, because remember that these are both 1/overs. So if you want to remove the minus powers here, you basically have 1 over this, and you have 1 over square root of all this. And so you can do a Taylor expansion to turn this whole thing into basically a polynomial. And Taylor expansions are something that you'll learn more about in a math methods course if you take it. But if you do the Taylor expansion, then this collectively ends up giving us an approximate answer of L times v earth squared over c cubed. What's nice about that Taylor expansion is that this is more obviously the correct units for time than is this. Although if you look here, you can see you have a length divided by a speed, that's a time, 1 minus a speed over a speed, or a speed squared over a speed squared, that's unitless. 1 minus a speed squared over a speed squared, that's unitless. So this also is units of time. So this is your approximate value. This is kind of like your exact value as predicted by the theory. Now, this maximum time difference, that's the difference in time between two arms for a given rotation or orientation. If we rotate everything by 90 degrees, what happens? Well, then we basically have a relative time shift between the two arms of 2 delta t max. So basically what we've done is we've gone from diagram 1 to diagram 2 in our Michelson diagram. So here's diagram 1, here's diagram 2. And that introduces a total difference in time relative between the two of 2 delta t max. And that introduces in some sense a path length difference of 2 delta T max times whatever speed light happens to be traveling at. In other words, c. And so, in turn, we now can figure out how much phase shift we have. So delta of phi, the phase shift, should look like 2 delta T max c, the distance we have, divided by lambda times 2 pi over, just times 2 pi over lambda is the factor. Or if you prefer, in number of fringe shifts, delta, let's say n, number of fringe shifts, this will just be 2 delta T max c over lambda. So we have our delta T max, now we have our fringe shift. So from there, maybe we want to figure out how many actual fringes are going to be shifted by the experiment. So let's kind of have like a for what it's worth. By using sort of multiple passes between two mirrors, the effective arm length L was about 11 meters for this experiment. The actual length may be 1 meter, but they used like a set of mirrors so that they made multiple reflections back and forth to extend this to 11 meters. That's a trick, by the way, that later in some sense became replaced by what's called a Fabry-Perot etalon, which, as it turns out, is still today used along with the Michelson interferometer for very high precision experiments. So they basically increased or improved their level of precision by making this a longer distance via these multiple reflections, and then they also got rid of any error in Earth motion by rotating the whole thing by 90 degrees. So, now we might ask, as an example, to calculate just how many phase shifts we expect. And we can do both the approximation and the sort of exact treatment if we want. So let's work a set of examples here. We can do one with the Earth's speed about the Sun, maybe another one with the Earth and Sun speed about the galactic core. We'll use white light since that's what was used in the original experiment, but we'll approximate this as 560 nanometers and work it out. As a basic reminder, we do know what the speed of light is, but we're just going to approximate it as 3 times 10 to the 8 meters per second because the other units that we have here don't have any further precision to warrant all these digits. So in sort of either case, what we're doing is calculating a delta T max and then using that to sort of step through and calculate the delta N given L equals 11 meters. So we can kind of use that L equals 11 meters here as well. And let's see how many fringes we predict for each of these two cases, and then I'll tell you how many they actually measured, bearing in mind that they had a precision of 0.01 fringes. So in both cases, we're using this equation for our delta T max, and if you'd like, you could go in and use the approximate equation here for your delta T max and see how they compare to each other. So in A, we're using this as V Earth. This is sort of part A. This right here is V Earth. for part B. So what we have is 3.0 times 10 to the 4th meters per second divided by 3.0 times 10 to the 8 meters per second. And so that ends up basically just being 1 times 10 to the minus 4, and there's no units because the units cancel out. For part B, you get an even you get a slightly larger number. So V earth over C becomes 2.3 times 10 to the 5 meters per second divided by 3.0 times 10 to the 8. Oops. That's an 8 for what it's worth, meters per second. So that ends up being about 7.7, if you're keeping your 7.67, something like that, 7.7 times 10 to the minus 4. So that's what we're plugging in to this equation for each of these two. So for our delta T max for part A, we have 2 times 11 meters divided by 3 times 10 to the 8 meters per second times 1 over 1 minus basically 10 to the minus 4 squared minus 1 over square root 1 minus 10 to the negative 4 squared. So you could call that just 10 to the negative 8 in both cases if you'd like. So just 10 to the minus 8. And so that you can throw all that into your calculator. What you end up getting is, so plugging in, and I'm giving intermediate values because this one right here is going to get recycled for the next part B problem. But you get this, and so then if you multiply all this out, what you get is a delta T max of about 3.66, sort of repeating, times 10 to the negative 16 seconds. Now, from there, what we wanted to do was calculate the delta D, so we're going to have to multiply that by 2 times C. So delta D is equal to 2C delta T max. So that's 2 times this number that we just computed times 3 by 10 to the 8 meters per second. So this obviously is going to give us a number that's on the order maybe 10 to the minus 7 or so. So this is 3.66 repeating times 10 to the minus 16 seconds. Let's multiply by 2, multiply by 3, multiply by 10 to the 8th, and what we get is about 2.19 repeating times 10 to the negative 7 meters. So if what you're wanting to get now is the number of fringe shifts, well, this top part is the distance we just calculated. We got to divide by lambda. So lambda, again, is given as 560 nanometers, or if you prefer, that is 5.6 times 10 to the negative 7 meters. So to get the delta N for this thing, that is going to be delta D over lambda, and that is going to be 2.1999 times 10 to the negative 7 divided by 5.6 times 10 to the negative 7, both in nanometers. So basically what that ends up giving us is approximately 0.393 fringe shifts. So if you have a resolution of 0.01, probably this last digit can be ignored, this is still 39 times the resolution limit. Should still be fairly easily detectable. For what it's worth, if you use the approximation obtained via the Taylor expansion, this term here, then you get about 0.44 phase shifts, or should get around 0.44 phase shifts or fringe shifts. If we want to use the speed of the Earth and Sun around the galactic core instead, then we replace the old 1 times 10 to the negative 4 term here with a 7.7 times 10 to the negative 4 term, and so propagate the math through. What you'd get is about 2.82 times 10 to the minus 15 seconds for the time. Then for the distance, you take this time and multiply by 3 times 10 to the 8. You get 8.47 times 10 to the negative 7. And so for the fringe shift number, which again is delta D over lambda, you have 8.47 times 10 to the negative 7 divided by 5.60 times 10 to the negative 7, both in meters. And so what you end up getting is an expected fringe shift of 1.51. Okay, so again, many times, in this case 151 times the resolution limit, again easily detectable. So what did they actually measure as their result in this experiment? They measured a fringe shift of 0. So they actually didn't measure any fringe shifts in this experiment, which they concluded basically meant that there is a ether speed of 0 relative to the Earth, which essentially means that you either have a totally dragged ether, and there were some theoretical reasons for why, and even observations for why that shouldn't have worked. Again, Fizeau's experiment with water and the speed of light in water kind of suggested that if there was an ether, that it shouldn't be totally dragged by the Earth. Second possibility is that the Earth isn't dragging the ether, but the Earth isn't really moving at all. And, you know, we've had hundreds of years of the Earth should be moving, both about the Sun and then about the galactic core now. There is a small group of people who still hold that maybe the Earth is somehow the center of mass of the entire universe and thus is stationary. So that's, I suppose, a possibility, but it seems like a very remote one. And then the third possibility is that there is no ether. So the conclusion that they drew from this experiment, to their surprise, was that the ether was being totally dragged, or that it was at rest relative to the Earth. And then it took Einstein's looking at these results and other things to formulate his special theory of relativity to suggest that there just is no ether. So today's video was pretty long, with the examples, with all the math, with all the explanations and everything. And that makes this lecture on the Michelson Morley especially long. So hopefully you enjoyed it and learned a lot from it. And thanks for watching.